Next up, we have inverse functions to look at. Here are our old friends, set A and set B. We know a function pairs something from A and something from B together. So I will go ahead and make some pairs here. We'll say 1 goes with 8, -3 goes with 0. We'll have a red car, and 5 square root of 3. There's our function. An inverse function is going to be a little different. An inverse function is going to start at B and go to A. So our inverse takes 0 to -3. It takes car to red, 8 to 1, and square root of 3 to 5. That is our inverse. So if we look at our original function, A going to B, sometimes we say this is A mapping to B. That's the more technical term. We can write these as ordered pairs. 1, 8, -3 was 0, 5 was square root of 3, and red was car. But now, for the inverse, we have B going to A. So now, instead of 1, 8, we have 8, 1. We have square root of 3, 5. We have car, red, and we have 0, -3. If we were able to graph these two graphs would not match up. It's very clear just with our first set of ordered pairs here. Right 1 up 8 is not the same thing as right 8 up 1. So we get two different graphs here. But you can see sort of what happened when we went from the original function to the inverse. All the ordered pairs got flipped. That's a key point. You may recall that a function is allowed to have repeated y values. But when we flip x and y, repeats are going to get us in trouble. For instance, let me make a new function down here. We'll call this C and D. Let's say I have 1, 2, 3, -1, 5. So we do this, we do this, and we do this. And that is a function. That is a function. Every x gets 1 y. There are no double arrows. There are no arrows coming out of, start over. Every x value has 1 arrow. No x value has 2 arrows. Y values, we don't care if they have 2 arrows. So I can say that this is a function. Well, let's reverse it. -1 goes to +1. -1 goes, uh-oh, that's a problem. Now we have it, when we flip that order, why did I put A, B? That was brilliant. You've been confused for the last 30 seconds. Apologize. There we go. Now we got the right sets. When we go in reverse, we no longer have a function because now we have 2 x values, and these are x values, even though they're coming from this set. If we're starting there, we have to treat it like an x value. Now we have a problem. We have two x value. We have the same x value with two y's. Not a function. So here we have a problem. What is the difference between this setup and this setup? This top setup is 1-to-1. Every x has exactly one y, and every y has exactly one x. That allows us to reverse the order and not have any problems. Here, we do not have 1-to-1. We don't need 1-to-1 to be a function. Going from here to here is a function. Going from left to right, that's a function. Every x gets one y. I don't have two arrows leaving any one number. But if I reverse the procedure, now we have a problem because this y value has two arrows coming to it. It's not reversible, which means the reverse is not a function. And it's not a function because the original setup was not 1-to-1. So, when can we reverse, or the actual term is called inverse, a function? When it is 1-to-1. And that is what these are called. These are called inverse functions. The notation for inverse is not f to the negative 1. That is not an exponent. That is simply a notation that means inverse. F inverse of x is the inverse of f of x. And oftentimes you will see this written as just f inverse with no parenthesis x. F inverse by itself, and f with the negative 1 by itself is considered good enough. So let's break down this definition a little more. What it means for a function to have an inverse means we reverse the process. We switch x and y. The domain of our function becomes the range of the inverse. And the range of our function becomes the domain of our inverse. In other words, they flip-flop x and y values. The original function's x's become the inverse's y's. And the original function's y's become the inverse's x's. Very important. The function must be 1-to-1 in order for it to have an inverse. It must be 1-to-1. Now that does not mean it's impossible if it's not 1-to-1. With some finagling, you can make functions have inverses. We know from earlier in the year that the sine of x, the cosine of x, they're not 1-to-1, but they have inverses because we use them to solve triangles. How do you find the angle when you're given two sides? You use an inverse sine or an inverse cosine. So there are inverses for sine and cosine. But they are very, very specifically and very strictly defined so that they end up being 1-to-1. In other words, the sine of x has no asymptotes. It is not undefined anywhere. There is nothing you cannot plug into the sine of x. The inverse sine of x has a lot of values that are undefined. It has a very limited range of numbers that you can plug into it. So you can make a non-one-to-one function have an inverse if you very, very tightly restrict what goes into that function. And that's something we will look at later on down the line. One final thing with inverses before we look at some examples. If we compose a function with its inverse, they completely undo each other. Here's a simple example. Think of a number. Double it. Add 1. Now write down that number. Now take the number you just wrote down, subtract 1, and cut it in half. You should be back to the very first number you started with. I just gave you a function, 2x plus 1, and I gave you its inverse, x minus 1 divided by 2. If you compose those two functions, you will find they completely knock each other out. Adding and subtracting are inverses. If I add 7 and I immediately subtract 7, I'm right back where I started. Multiply by a number, divide by the same number. They cancel each other out. A function and its inverse will cancel each other out when you compose them, and you are left with whatever you plugged in. It does not matter which order you compose them. Adding 6, subtracting 6 cancels out the same way that subtract 6, add 6 does. Multiply by 18, divide by 18. Divide by 18, multiply by 18. It doesn't matter. Squaring and square roots are inverse. E to a power and natural log are inverses. The list goes on and on and on. Sine and inverse sine, obviously they're inverses. Lots of functions have inverses, but again, not every function has an inverse defined everywhere. Sometimes we have to restrict things for it to have an inverse. For this lesson, though, we're going to focus on the ones that are one-to-one only. One final thing about inverses, then we'll look at some examples. Here I have a blue dashed line. This is the line y equals x. I also have this red function that's graphed. And you can see that it's one-to-one. It passes the vertical line test so that it's a function. It also passes the horizontal line test, so it's one-to-one. If you have the graph of a function and you put this line y equals x in, you can graph its inverse, because a function's inverse is symmetrical to this line. In other words, think of this as a mirror. We're going to take this red graph and flip it over the blue line. So if we are above the blue line, for example, from here to here, from this point to this point, we are going to now be below it. And we are going to rely on my artistic skill here. That's a little off. That's kind of sort of what's going on. From this point on down, the function is going to be below the blue line. So its inverse is going to be on this side of the blue line. And I can repeat that for the rest of this here. That's off just a little bit. You kind of get the idea. This part's going to be a little tricky. I have to sort of bend in a little bit and then curve. And there we go. There's a graph of the inverse. If you imagine this as being a mirror, here is the inverse of the red function, kind of, sort of. It is a mirror image of it. And notice that the green graph passes the vertical line test, assuming that I did this exactly perfectly, which I don't really think I did, but it's close, and it passes the horizontal line test. Here's a function that does not have an inverse that's readily available. And that's x squared. Here's why it doesn't have an inverse. At least not a nice one yet. I'll do the inverse in green. From here to here, we are like so. And then from here to here, we are like so. Let's see. If I can do this correctly, it should be like this. There we go. Actually, no, that's not correct. That is not correct. This should be more like, there we go. And this should be more like this. So you can see that its inverse, first of all, is not a function. It's going to fail the vertical line test. This green graph fails vertical line test. Its inverse is 1-to-1. But it's not a function, so 1-to-1 doesn't even apply. The original graph is a function, passes the vertical line test, but it fails 1-to-1. And it's going to fail 1-to-1 and not have an inverse because its inverse no longer is a function. So here's what we do. I'll give you a little preview of what's coming later on. We say that, let me write it this way. We say that f of x equals x squared, but only when it's greater than or equal to 0. So now we have half a parabola. That's 1-to-1. That's 1-to-1. Passes the vertical line test, so it's a function. It passes the horizontal line test because I chopped off this entire half. I said x is only allowed to be 0 or bigger. Now I have an inverse. And that inverse is, inverse of a squared is a square root. What if I want the other half of the parabola? What if I want everything else? Well, the square root of x is only defined over here. I can't plug a negative into a square root. So that's why we define this the way we do. This is defined like so in order to get an inverse. Now, we are not saying that this goes away forever. We're only saying for the purposes of an inverse, we are restricting this to allow this to happen. In general, this is still a parabola. It is still a U-shaped curve. But for finding an inverse, we say we completely ignore this part because we can't plug in negatives anyway. We can't we can't have something that doubles back on itself. If I go back to the original graph here that I attempted, here's the part of the graph when x is a negative number, and it breaks our vertical line test. So we'll spend some more time on that in a future lesson. Here I have two functions. I claim they are inverses. Our task for this problem is to prove it. And it's very simple to prove. We know that f of g of x has to equal x. And g of f of x has to equal x. We know that both of those have to work. So let's start with f of g of x. We're going to plug g into f and see what happens. The rule for f says whatever's inside the parentheses, we multiply by 2. Then we add 3. And I'm going to leave the details to you because this is something that every pre-calculus student should be able to handle at this stage. Yes, it comes out to be x. Flip it around. We should get x again. G of 2x plus 3 should come out to be x. Let's see what happens. The rule for g, whatever's in the parentheses, gets plugged into the numerator. 2x plus 3. We subtract 3, we divide by 2, and yes, we get x again. That is how we prove functions are inverses. So we've seen inverses graphically, we've seen inverses as sets, we've seen inverses that work out. Now it's time to find an inverse. Here's a function, 1 minus 2x, find its inverse. I'm going to back up a few pages here to this graph. Actually, let's go all the way back to the beginning. Let's go back to here. When we went from A to B and then from B to A, we saw what happened. The x's got switched with the y's. That's our key to finding an inverse. Instead of f of x, I'm just going to write this as y equals 1 minus 2x. And now, we do a little magic. I'm going to replace x with y and y with x. I'm going to flip them. And now, our goal is to get this y all by itself. So, once we switch x and y, we do whatever operations we have to do in order to get y alone. And of course, yes, you need to follow the correct order of operations. You need to still do the algebra correctly. You need to do things in the correct order. Now we're just solving for y all over again. And when we get to the end, we will have our inverse. I will leave the details to you. And you should get this as a result. X minus 1 divided by negative 2. Check. Let's check that. F of g of x. We only need to check one. If it works for one, we will assume it works for the other. F of Actually, instead of f of g of x, let's do this. Let's say f of f inverse of x. F of, we're claiming that our inverse is x minus 1 over negative 2. Plug that into the rule for f. 1 minus 2 times x minus 1 over negative 2. And let's see what happens here. Cancel, cancel. 1 plus x minus 1. We got x, therefore this is our inverse. And to finish this, we typically write it f inverse like so. We take the y out and we put in f inverse just to notate that we found the inverse of something. This function is the inverse of this function. Crank things up a notch. Find the inverse. First question is it 1-to-1? If it's not 1-to-1, we have a problem. How do we know if it's 1-to-1? We all have this nice little tool here. So let's use the tool. Let's try that again. Use the tool to determine if it's 1-to-1. And it appears that it is. Yeah, that looks a little horizontal there, but understand that a polynomial is never exactly horizontal. It's really close to horizontal. If I zoom in on that spot, and then I hit trace, the y values will change a little bit. Now again, here it looks like these are the same, but understand that your calculator is only rounding these values to a certain level of precision. It's basically saying that these y values are so close, they're so close that too many decimal places are required to show the difference. So rounding to what's on the screen, these look like they're the same, but they're not really. It's just that the level of precision is so far down, so far to the right of the decimal point that the calculator can't show that. So it's just taking the short way out and saying, yeah, they're about the same. But there is a very subtle difference there in the y values. So for our purposes, this is 1-to-1. Because it's 1-to-1, it has an inverse. Change the x and y around. And now we will solve for y. And we will end up with this. The fifth root of 2x plus 3. Here's the inverse to our function. And if we compare this to the original, we see that they are likely going to be inverses. We have a fifth power. Here's a fifth root. Here's a minus 3. Here's a plus 3. Here's a divide by 2. Here's a multiply by 2. It has all the elements that an inverse requires. Every operation in the function is undone by some operation in the inverse. Not in the same order, but they will all be undone. One final example to take a look at. Wrap up this section. Again, this is a 1-to-1 function. We know it's 1-to-1. If you're not convinced, graph it. It is 1-to-1. It looks like we have a gap here. We have an asymptote here. 1-to-1 passes the horizontal line test. So this does have an inverse. Whoa, I did that wrong. There we go. Those are x's. Now we switch the x's and the y's. If we cross multiply on both sides, or we just cross multiply, we get x times this quantity is equal to this quantity, which is multiplied by 1. And now I have to do a little finagling. We got to get y equals. So what I'm going to do is get all my y terms on one side. And get everything that doesn't have a y on the other side. I'm going to factor out a y. And now I have a quantity that I can divide by both sides. There's our inverse. Minus 5x over negative 2x minus 3. It's a little weird, but that is the inverse for this function. Another way to write it is if you divide everything, if you multiply both top and bottom on the right-hand side by negative 1, you could say it's 5x minus 1 over 2x plus 3. You could do that as well. So if we compare that to the original, we have a times 3x, or times 3 here, and there's a divide by 3 hidden there. And a lot of the things, because it's a rational function, a lot of our operations are going to be sort of hidden. So it's not as explicit as the last one was, because things look a little differently. So here I have a 1 plus, well, here I have a minus 1. Times 3, I have a 3 in the denominator. 5, that's positive, and that's sort of hidden down here. So there's a lot of subtle differences, but this is the inverse of this. They are inverses. That wraps up this section. You know what to do from here on out.